Do you know that the crew of NASA's Apollo 13 mission swung around the far side of the moon and traveled 248,655 miles away from Earth? You may know this, but have you ever thought about how we communicate with astronauts so far away? It might seem like science fiction, but communicating with spacecraft is a crucial part of space exploration. In this video, we'll explore the fascinating world of space communication and discover how we send messages and receive information across the vast emptiness of space. Radio waves were the earliest and most fundamental means of communication in space exploration. Spacecraft transmitted data back to Earth using radio signals, which were received by ground-based antennas. This method was used for both telemetry, which means transmitting data about the spacecraft's status, and communication with astronauts during missions. Then, in the early 1960s, NASA initiated the ECHO program by utilizing large metal balloons known as ECHO satellites in low Earth orbit as passive reflectors for communication signals. Signals were transmitted from ground stations to these satellites, which then reflected them to another ground station. This enabled long-distance communication. In 1962, NASA launched Telstar, one of the earliest active communication satellites. It facilitated live transatlantic television broadcasts and telephone communication by relaying signals between ground stations in the United States and Europe. Following the success of ECHO and Telstar, various countries began launching communication satellites into orbit. These satellites used onboard transponders to receive, amplify, and transmit signals, enabling a wide range of communication services, including telephone, television, and data transmission. Space communication efforts often involved international cooperation, with countries collaborating on satellite launches, ground station networks, and the standardization of communication protocols. Organizations such as the International Telecommunication Union, or ITU, played a role in coordinating and regulating space communication activities on a global scale. The first human space flight took place on April 12, 1961, as part of the Soviet Union's Vostok program. The mission was named Vostok 1, and the astronaut who made this historic journey was Yuri Gagarin, a Soviet cosmonaut and pilot. The spacecraft used for the mission was Vostok 1, a spherical capsule designed specifically for human spaceflight. Yuri Gagarin was launched into space on a Vostok K rocket from the Baikonur Cosmodrome in Kazakhstan. The spacecraft completed one orbit around the Earth, with the entire mission lasting approximately 108 minutes from launch to landing. A network of ground control stations, including the main control center located in the Soviet Union, was responsible for monitoring the mission and maintaining communication with the spacecraft. These ground stations were equipped with large antennas capable of receiving and transmitting radio signals to and from the spacecraft. The Vostok 1 spacecraft was outfitted with communication equipment, including radio transmitters and receivers, antennas, and voice communication systems. Gagarin used radios that transmitted via very high frequency, or VHF high frequency, and shortwave bandwidths. He tried to maintain communications with a network of 6 or 7 ground stations, all based inside the borders of the Soviet Union. Ground stations and the Deep Space Network, or DSN, are vital components of space communication infrastructure. Ground stations, also known as Earth stations or Earth terminals, are terrestrial radio stations designed for communication with spacecraft or reception of radio waves from astronomical sources. They use parabolic antennas to transmit and receive radio waves in super high frequency, or SHF, or extremely high frequency EHF bands. Ground stations can have fixed or mobile positions as outlined in international regulations. Specialized ground stations, such as satellite tracking stations or teleport hubs, serve specific functions like communicating with satellites or connecting satellite networks to terrestrial networks like the internet. Standards for ground stations are set by organizations like the International Telecommunication Union, or ITU, and satellite operators like Intelsat and Eutelsat. The Deep Space Network, or DSN, is NASA's international array of giant radio antennas operated by NASA's Jet Propulsion Laboratory, or JPL, supporting interplanetary spacecraft missions and Earth orbiting missions, as well as radar and radio astronomy observations. The DSN's 3 primary ground stations are located in Goldstone, California, USA, Madrid, Spain, and Canberra, Australia, spaced approximately 120 degrees apart in longitude to ensure constant communication with spacecraft as the Earth rotates. These facilities are equipped with large parabolic dish antennas and ultra-sensitive receiving systems. The DSN is responsible for commanding, tracking, and monitoring the health and safety of spacecraft across distant planetary locales, facilitating powerful scientific scientific investigations into asteroids, planets, and moons. The Apollo 11 mission, which successfully landed astronauts Neil Armstrong and Buzz Aldrin on the lunar surface in 1969, relied on a sophisticated communication system. This system primarily utilized NASA's Deep Space Network, or DSN, comprising 3 large deep space communication facilities located in California, Spain, and Australia. The Scottsdale-based team played a crucial role in manufacturing vital components for the spacecraft's communication systems, ensuring continuous contact with mission control during the mission. Messages between Earth and the Moon took approximately 1.28 seconds to travel one way, thanks to the use of radio waves moving at the speed of light. The communication equipment on board the Apollo 11 spacecraft include high-gain and low-gain antennas, as well as a VHF antenna on the lunar module for intra-vehicle communication and communication with mission control. Despite the lack of existing communication infrastructure on the lunar surface, NASA overcame this challenge by building ground stations, mobile stations, tracking ships, and aircraft around the world to maintain continuous communication with the spacecraft. The General Dynamics S-band transponder played a pivotal role in transmitting crucial data and commands between the astronauts and mission control. During Neil Armstrong's historic moonwalk, the transponder successfully relayed his iconic words and video footage back to Earth. The Mars Curiosity rover, officially known as the Mars Science Laboratory, or MSL, is a robotic rover that NASA sent to explore the surface of Mars as part of its Mars exploration program. Launched on November 26, 2011, Curiosity landed on Mars on August 6, 2012 in Gale Crater, a location chosen for its potential to provide insights into Mars's past habitability. Curiosity is equipped with several communication systems, including antennas and radios to transmit and receive signals. These systems include a UHF antenna for short-range communication with orbiters around Mars, and an X-band high-gain antenna for long-range communication directly with Earth. The rover transmits data to orbiters such as NASA's Odyssey Orbiter and Mars Reconnaissance Orbiter, or MRO. These orbiters serve as relay stations, picking up signals from Curiosity and relaying them back to Earth. NASA's Deep Space Network is a global network of large antennas and communication facilities located in California, Spain, and Australia. The DSN plays a crucial role in receiving signals from Mars missions, including Curiosity. It communicates directly with the orbiters and receives data from them, which is then relayed to mission control centers on Earth. Curiosity sends various types of data to Earth, including images, scientific measurements, and telemetry data about its health and status. The data is transmitted using radio waves at different frequencies depending on the distance between Mars and Earth and the type of information being sent. The future of space exploration is a collaborative effort between private companies like SpaceX, government agencies like NASA, and the ever-evolving power of artificial intelligence. Starlink's constellation of low Earth orbit satellites has the potential to become the backbone of the global internet infrastructure, even reaching remote areas on Earth. Artificial intelligence can analyze vast datasets to optimize mission planning. AI could identify potential landing sites, suggest efficient trajectories, and even predict potential hazards, leading to safer and more efficient space missions. AI can be trained to analyze data from telescopes and other scientific instruments at an unprecedented scale. SpaceX's Starship program aims to develop a fully reusable launch vehicle capable of transporting humans and cargo beyond Earth's orbit. This could revolutionize space travel, making missions to Mars and beyond more affordable and accessible. NASA's Artemis program aims to return humans to the Moon by 2025, with a focus on establishing a sustainable lunar presence. This program will provide valuable experience and data for future Mars missions. NASA is a key player in fostering international collaboration in space exploration. Partnerships with agencies like ESA, European Space Agency, and JAXA, or Japan Aerospace Exploration Agency, will be crucial for large-scale projects like establishing a Martian base. That's all the time we have for how we reach out and chat with our explorers across space. But our connection with the cosmos doesn't stop there. What kind of future advancements in space communication are you most excited about? Leave a comment below. And don't forget to hit that subscribe button to stay updated. Thanks for watching.